Okay, good morning. Okay, so if you remember last time we started a lesson, derivative of exponential functions. So far we have this. So if you remember, we are trying to find the derivative of famous functions. So the first famous function is the constant function. We realize the derivative is 0. This type of functions is called, they are called power functions. Power function means that the exponent is a constant and then you have x here. So then what do? If you want to differentiate, you bring this a down and then you multiply it by x to power 1 unit less. The goal of this lesson was to be able to answer this question, a to power x. What is the derivative of this function? This is different from that function. If you see here, the constant is in the base and the exponent is the variable. This function is called an exponential function. And we spent the whole lesson last time, but still we are not there to answer this question yet. So this will be the topic of the lesson today. But in the meanwhile, we realize that there is one particular number, e, which is actually called the Euler function, the Euler number. And then for that particular number, we were able to find the derivative of that exponential function. So it means that if a, which is supposed to be a positive number, a number not equal to 1, if this a happens to be the Euler function, the Euler number, we were able to find the derivative of the function. Okay, so if I want to remind you a little bit here. So we started with this question. A is a positive number. A is not equal to 1. And then my function f of x is equal to a to power x. We were supposed to answer this question, that what the derivative of this function is. So if you remember, we started from the definition of the derivative, which is this limit of f of x plus h minus f of x divided by h goes to 0. And then we wanted to calculate this limit. Instead of f of x plus h, we write a to the power of x plus h minus, instead of f of x, I write this, divided by h goes to 0. Then I can factor this out, so this becomes the limit a to power x, a to power h minus 1 divided by h. Why is that true? Because if I multiply this in, a to power x times a to power h will give me this, and a to power x times minus 1 gives me this. So that's correct. But then you realize that a to the power of x is a constant for this limit because it does not depend to h. I am changing h. I am making h smaller and smaller. Making h smaller and smaller will not affect this part because there is no h dependence there. So I could take this out and multiply it by this limit. H goes to 0. And the problem in front of us was how to calculate this limit. So that was the hard question. Because we do not have enough theorems about limits, we have to go around the problem. So we cannot directly at this level tackle how to solve this problem. Okay? So this is why it makes it so long. Otherwise, I could calculate this limit for you, and that would be the end of the story. Okay, but at least, if you remember, I said that, okay, we don't know how to calculate this. Let me call it L. For the time being, we know that the answer to this question mark is this. Is a to the power of x multiplied by a constant. And this constant is the limit of a to power h minus 1 divided by h goes to 0. So far, we got this. Yes, this L is the value of this limit. We know that this is a number at the end, a constant number. So that is first of all interesting to see that if I start with an exponential function, its derivative is more or less the same function, at most multiplied by a multiplicative constant. But that is good to know. And then you remember, we calculated this limit for two particular values, not calculated, motivated us that what will happen. So for understanding this limit, we once chose a to be 2, and then calculate, set up a table of values for this function. So I mean that I chose a smaller and a smaller values for h and used my calculator to calculate the value of this fraction. And I realized that this limit apparently is less than 1. I didn't calculate that. I just calculated the value of this fraction for a smaller and a smaller values of h. And I realized that these values are being stabilized around a number which is less than 1. And then I chose a to be 3. And then I did the same thing for this limit. I was able to convince myself that this time these numbers are stabilizing around a number which is larger than 1. So I concluded that this limit, whatever it is, if it exists, it is larger than 1. Then, of course, having these two motivated me might be there is a number for which this limit is exactly 1. Yes? So then we define that number the Euler number. So if you ask me what the Euler number is, I would say that the Euler number is that unique number for which this corresponding limit is exactly equal to 1. So this is the definition of the Euler number. So the Euler number, which we denote by E in mathematics, is that unique number. The existence of that, the uniqueness of that, they are mathematical problems. In principle, in rigorous mathematics, you should address them. But at this level, you need to take these things for granted, okay? So we said to ourselves that, okay, this motivates me that there might be a number for which this particular limit is exactly equal to 1, and I call that number E. So this is also important to realize. This is one of the famous limits in mathematics. So this limit is 1. And then using this, I was able to find another formula for E. So if you follow the videos, you will realize that E becomes the limit of 1 plus h, 1 over h goes to 0. I actually derived this more or less for you. And if you use this to approximate E up to 2 decimal points, E was what? E was 2.72, up to 2 decimal points. And I also told you that in higher mathematics, you can prove that E is also irrational. It's like pi. So this is the Euler number. Okay, so now what does this mean? This means that if I have started from e to power x, not just any a to power x, what will happen? If f of x is e to power x, then if I ask you what the derivative of this is, the derivative is the same function but multiplied by this limit. So this becomes the same function itself multiplied by that limit. But that limit for a when a is equal to e. Yes, do you understand this? So that was the content. So this is the completely general formula for any a as far as a is positive and not equal to 1. So if I use this formula by replacing a to e, then I will get e to power x rather than a to power x. This becomes e to power x multiplied by this limit in which a is replaced by e. But what this limit is, based on the definition of the Euler number, this limit is 1. So this will give me e to power x. Yes. So this is a very, very interesting function. This is a function whose derivative is exactly equal to itself. Okay. And then we actually improve this general. We actually extend the problem to this type of functions. So this I want to skip. I did it completely when I was teaching it. So we can show that if we start with this function, so that this c is a constant, the consequence of this constant would be that the derivative of this function, c goes down and the function repeats itself. So that is also, right now I'm skipping the proof of this, but the proof of this we did the last thing in the last session. So this is what we have so far, yes? Is that clear? Okay, so let us practice a little bit about these two rules. But I want you to know that I started with this question mark, but this question mark still is not answered. Okay, we have to answer it today. But before continuing, let me just refresh your memory. I told you that this long lesson, what matters at the end, if you are only considering about the exam, is how to use the formulas to differentiate. Okay, so let me give you some examples before continuing to the new lesson today. Differentiate the following functions. So for example, let me write number 1. F of x is equal to 1 over 4 e to power x plus 1 over 4 e to power minus x. Okay, so these are very simple problems. So if I want to differentiate this, let me just do it once again. You don't need to write all these details. It's better to skip them. But let me just do it once more like this. So when I ask you to differentiate this function, I mean this. And then which rule is applicable first? This rule, yes? This is called the addition rule. This rule tells me that if I have the sum of two functions and I want to differentiate the whole sum, I am allowed to do it separately. So this means that this is one function, this is another function, they have been added. I want to differentiate, so I am allowed to differentiate the first one. I am allowed to differentiate the second one and add the results. But again, now the first rule is applicable because I have a constant multiplied by a function and I want to differentiate the whole product. This will tell me that do not touch the number, just take the derivative from your function. So what you need to do, as I told you, I really don't want you to write this because it takes unnecessary time. But this is the way that you have to think. Okay, and then now the lesson is clear. So what is the derivative of e to power x? We just learned that this is the function itself. Okay, can you tell me what is the derivative of the second one? The derivative of e to power minus x. What is that? Yes, that is correct. Why? Because e to power minus x, e to power minus x means what? Means e to power minus 1 times x. So when I want to differentiate this, it means that I want to differentiate this. So if you compare this one with the formula that I have written here, Minus 1 here is playing the role of that c. So minus 1 goes down, and the function repeats itself. But no one writes like that. That's an easier way to write it. That's just minus e to power minus x. So then this minus sign that goes down, I will take it out. So this becomes this. Is that clear? Okay. So it is a good idea if I can also add these two here. So some special cases, if I want to write the special cases of this, you can say that the derivative of e to power x is equal to itself exactly, and e to the power of minus x derivative is minus e to power minus x. Okay. Another example, number 2. So what should I do here? F of x is e to power x over 2 plus 5e to the power of minus 3x plus 2x squared plus 1. Okay, so I want to differentiate this function. I will do it faster this time, okay? So if you want to differentiate this function, what we are supposed to do, so the derivative becomes equal to, okay, the derivative of the first one. So how do you interpret this? How should I interpret e to power x squared, x over 2? E to power x over 2 means e to power 1 over 2 times x. Yes? And then it means that this 1 over 2 is playing the role of this c. So c goes down and the function repeats itself. Okay. So this means that if you want to take the derivative, c goes down. What is my c in this problem is 1/2, and the function will repeat itself. Yes? And the next one, minus 3 plays the role of the constant c. So minus 3 goes down, there is a 5 there, multiplied together, minus 15, and the function repeats itself. And the next one is just a polynomial function. So this becomes 4x, and the derivative of 1 is 0. So that is the derivative of the function. One more I think is good. Let me write one more. So number 3, f of x is equal to e to the power of 4x multiplied by e to the power of 3x plus e to the power of minus 3x totally squared. Okay, I will wait a little bit for you so that you can solve this yourself first. So we want to differentiate this function. Okay, so let me now solve that because we want to continue the lesson. So at least you can tell me where should I start from? What's this first step? What? Yeah, we have to expand that because we have the power of 2 here. So we expand the first. Expand this using the quadratic or squaring rule, yes. So I copy and paste this part for the time being. Okay, the first one squared gives me e to power 6x plus 2 times the first one times the second one, and then plus the second one to power 2, which gives me minus 6x. Yes? But this one has a better name, yes? What is the answer to this part? e to power 3x times e to power minus 3x, it's 1 because it becomes e to power 0. E to power 0 is 1. And then I multiply this again in. So f of x is equal to e to power 10x. When I multiply this in here, e to power 4x times 2 times 1 becomes 2e to power 4x. And then finally I multiply this there, it becomes e to power minus 2x. And now everything is ready, so I can differentiate. This 10 is playing the role of that c. 10 goes down and the function repeats itself. 4 goes down and the function repeats itself. 4 times 2 is 8. Minus 2 goes down and the function repeats itself. So that's the derivative of this function. Okay. So this way of presenting this is a little bit convoluted. So remember that still we were not able to answer. So I want to start a new lesson now. So we still don't know this limit. Momentarily we give up. We actually start doing something else, and then we come back answer this limit in a very indirect and convoluted way. In order to answer that question, we need to know a little bit about logarithms. So I want to review very briefly what logarithm is from Math 2C, and then start the new lesson. So do you remember what was the, so let me write here logarithms. Review, yes. So this is the review from Math 2C. So what is a logarithm? So assume that you have a number a, which is positive, and you have a number b, which is also positive, but this b should not be equal to 1. Okay, under these circumstances, we can talk about logarithm of this number a to the base b. Yes? So this is equal to a number x if and only if what happens? B to power x is equal to a. So do you remember this was the idea of a logarithm? When you say logarithm of a to the base b is x, it means b to the x is a. That was the definition of the actually logarithm. So for example, we know that if I ask you what is the logarithm of 16 to the base 2, what's the answer? The answer is 4, since if someone asks you why did you answer 4, we say because 2 to the 4 is 16. Yes? And for example, logarithm of 1 to the base 5 is what? 0, since 5 to the 0 is 1. I don't know, for example, logarithm of the square root of 2 to the base square root of 2 is, what is this number? 1, since square root of 2 to the power 1 is indeed equal to this number. So that was the meaning of a logarithm. And of course we had a remark, do you remember? If this base is 10, if b is 10, we don't write it, yes? So when you see logarithm of a without any base, this means logarithm of a to the base 10. Yes, that is just the remark we had before. So what I want now to do is to review only formulas for the logarithms we had. Okay, so important properties of logarithms. Let me write them in a way because I want to, okay, important properties of logarithms. Okay, so number one, if actually, so we can say that the logarithm of 1 in any base b is what? Is 0. Of course, b should be positive, not equal to 1, because otherwise this is not defined. So logarithm of 1 to any base is 0, yes, because b to power 0 is 1. Another thing is that logarithm of b to its own base, if b is positive and not equal to 1. What is the answer to this? It's 1. Number 3, which is probably a very important one and plays a vital role here in this discussion, is actually the definition of the logarithm itself. So if I ask you, what is b to power logarithm of a to the base b? What's the answer? This is a. Yes, this is a itself. Of course, b should be positive, b shouldn't be equal to 1, a should also be positive. Why is this true? It's very simple, yes, because instead of this x that you see here, you can plug this back, yes, so it becomes b. Instead of x, you write this expression, and equal. On the right hand side you have a. So it is nothing except the definition of the logarithm written in a little bit more convoluted way. So this tells you that if you raise b to the power of a logarithm whose base is also b, then everything is cancelled out and a is left. Is that clear? Okay, so number 4. We remember that we had this. Do you remember logarithm of a product? What will happen if I have a base b? Then it becomes logarithm of x to the base b plus logarithm of y to the base b. Of course, we should have x positive, we should have y positive, and we should have b positive and b not equal to 1. Under all these circumstances, this formula is valid. And 2 more, do you remember what are they? Number 5 and number 6. So what are they? Yes? Subtraction for division, yes? So logarithm of x over y to the base b is logarithm of x to the base b minus logarithm of y to the base b, of course under the same conditions. And finally there is one more. What is that? No, just the famous ones. Yes.
Log of a with the base b, no, log of a to the power of
Yes.
c.
Exactly. So logarithm of, I don't know, a to some power p to the base b. P goes to the back of the log, yes? So it becomes p times logarithm of a times the base b. So here, P is any real number that you like, but B should be positive and not equal to 1. Of course, A should also be positive. Okay, so that is what we had before in Math 2C for the definition of logarithm. Now we want to define the new lesson. This is the new lesson. We want to talk about the natural logarithm. Okay, so what is the natural logarithm? For the time being, if you don't mind, let me clean here. Might be we need this. So natural logarithm is of course also very, very simple. So do you remember I told you that if the base is 10, we don't write it, and we use this simplified notation for that. Now, if the base is the Euler number, the logarithm is called the natural logarithm. As simple as that. Okay, so I would say that let A be a positive number. The natural logarithm of A is denoted by, this is the symbol we use, ln of A, and it's defined as follows. And it's defined by, so when you see people write ln of A, they mean logarithm of A to the base E. And the base E is the Euler number. So that's the definition of a log. Yes? No, I don't know why I write it big L, yes. Sometimes I extend that. Yeah. So ln of A is nothing except logarithm of A, but the base is E. First of all, is E an acceptable base? Yes, because for the logarithm to make sense, the base should have two properties. It should be positive, it should be not equal to 1. So it is completely acceptable to choose E as the base, because E is, remember, 2 point something. So it is positive and not equal to 1. So first of all, this is acceptable as a base. On the other hand, yeah, this is the definition of the natural logarithm. So working with the natural logarithm is much easier than working with logarithms. I don't know, might be I have used to it by using it so much. For me, it's easier to work with natural logarithm rather than the logarithm itself. So natural logarithm is denoted by another symbol. Instead of writing log to the base E of A, we summarize it to this. But the good news is that what property you had before, you still have it. Yes, because that's a logarithm. And I want to write all the counterparts of these formulas for the natural logarithm to practice a little bit. Okay, so I want you to help me for that, okay? So, for example, let me change my color here. And I want you to write for me the counterparts here, yes? Properties, important properties of natural logarithm. Okay, so now can you help me to do that? So number one, I want to write something which is similar to this one, but for the natural logarithm. So what should I write? I change b to e. So then what happens? It becomes ln of 1 to the base e is 0. But I told you just now that no one writes ln of 1 to the base e. People simply write ln of 1. So the first formula I want you to know is that ln of 1 is what? 0. So ln of 1 is 0. What about this one? How do you read this in this new context? You change b to e, so this becomes ln of logarithm of e to the base e is 1. But instead of writing logarithm of e to the base e, people simply write ln of e. Okay. So ln of 1 is 0. I don't remember are they given in the formula sheet or not, but I want you to know at least. ln of e is 1. So how this formula, which is the probably most important for our case here, how this formula reads, instead of b you put e. Then what happens? Number 3, it becomes what? E to the power of logarithm of a to the base e is a. If you want, I can write it. Let me write and clean it. Instead of b everywhere, I put e. Do you agree? Instead, I change b to e, I got this. But instead of this, what can I write? I can simply write ln of a. So this becomes ln of a, and this becomes a. It's this very important formula. E to power ln of a is a. So number 4, how this formula will read. Again, I change b to e. So this becomes ln of xy is equal to ln of x, which you usually don't put brackets around that, plus ln of y. But still, I should have these conditions. So it is extremely important, be careful, x and y should be both positive. And number 5, I will change b to e, I will get this formula. And x and y are positive. And finally, number 6, ln of x. So ln of a to power p becomes p times ln of, and of course here p is any real number that you like, but a should be positive.
Natural logarithms used for?
You will see now. I will use it to find the derivative. At least in this way of it presenting stuff, something becomes clear. It's natural that we want to talk about these things. Okay, so now can you tell me how can I use it? Because I want to test your understanding. You still remember what is my question? My question is that I want to answer what is the derivative of a to power x? We can solve it now, finally, by the use of the natural logarithm. How? Let us go back here. So let me clean this. And now let us go back to our question. Okay, so let me write the question again here. The question was this: f of x is equal to a to power x, yes, where a is positive and a is not equal to 1. My question is that what is f prime of x? You want to answer this question. And I completely now ignore what I described here. Yes, so we will not be able to calculate the limit still here. But we can use the information that I provided here for you to be able to answer this question finally. And you see how. And this formula plays the vital role. Yes?
e to the power of x of ln a
Oh, is what?
is equal to a to power.
Yeah, exactly. That we can solve. Why we is solve? Because a is equal to e to the ln of a. Yes, so what I do, I rearrange this function in a slightly different way. So I say that, okay, instead of this a, I am allowed to write e to the ln of a. And then I have power of x. Okay? But we know this rule for exponentiation. This exponent, another exponent, so I multiply the exponents. So then it becomes e to the power of ln of a multiplied by x. And I think that you know this is solved now, yes? Because compare this with the one that we already had, and we proved that, yes? So this c plays the role of this ln of a. This ln of a is playing the role of that constant c. So if I ask you, do you know the derivative of this function? You would say yes. What is the derivative of this function? This is playing the role of the constant, so it goes down. Yes? And then the function repeats itself. Do you agree? But then, if you don't mind, we don't need it anymore. We write it back into the original form. What is this one? That was a to power x. Yes? Because a to power x, I wrote it in that way, and I use this, and I don't need any more. So I just write it back. Of course, you can keep it like this, but I would prefer to write it in this form because this is much more compact. Is that clear? So if you want, let me write it like this. A to power x is, so might be this is better way. A to power x is e to power ln of a to power x. Then it becomes e to power ln of a multiplied by x. Yes? And then instead of differentiating this, I differentiated this one, and I got this answer. But now you see that instead of this, I can put this back. So I wrote x to the power of x. So what happens? This becomes ln of a multiplied by a to power x. So this is finally the question, the answer to the question mark. So now I can complete this. So I clean this question mark here and write the answer. So what is the answer? The answer is, let me write it the other way around. The function repeats itself, but in this case, the function repeats itself, But in this case, the function not only repeats itself, but you need to remember to multiply it by an ln of a. Of course, in this case, we can use this rule as well. But because e is a, so then ln of e appears. But ln of e is 1. So you can say that this formula is also working for this case as well, naturally. But usually it is better to have them. So I mean that if you just know this, that is enough even for e to the x. Because in that case, a is e, but ln of e is 1, and I will get the same formula. So finally, we were able to answer that question. So the derivative of a to the x is the function itself multiplied by a mysterious constant, which is the natural logarithm of the base. But I don't know, you should, if you like mathematics, probably you should be still disturbed by something. What is that something? No, we answer that, yes. That is some disturbance, but that is something we can answer. No, because you know that we somehow it seems that we lost the logic in the middle of the way. Because the way that I started, this is still on the board. This is the reason that I didn't clean that. So what was the problem? The problem is that I was supposed to calculate the limit. That was my motivation first. I did it partially for e, then I didn't use it at all to get the derivative. So still one question is left. Either we can answer it or we leave it for higher mathematics. So what that question is, there is a question still to be addressed before even going to the second question mark. What that question is? That
limit is ln of
that,
e.
yeah. What is the limit? Yes. So still we haven't calculated the limit. So now we change the logic. We usually need, in principle, we have to calculate the limit to answer the derivative. But for some reason that I tried to make it plausible for you, we were able to find the derivative before calculating the limit. Now we can equate them and then find the limit. I mean, the logic is completely different, but this makes sense, hopefully, yes? Because the natural way to do this was to do this. And this, by the way, if you go to a little bit higher mathematics, no one will do it in that way because people know how to calculate this limit. Yes? But for this lesson at this form, we already knew this, but now compare the derivative. Now, if I ask you, do you know the answer to this? Right now you say yes, because the answer here is on the board. So it is ln of a times a to power x. I put it instead of derivative. This is equal to a to power x times L. So if you compare this, what does it mean for L? This means L is what? ln of a. Yes? And by the way, this is why you couldn't guess what is the answer to this limit by looking at those numbers. By looking at the numbers in the table I presented last session, we realize the number of these, the numbers are getting close, smaller. And so you realize that they are being stable around a number less than 1. But you couldn't guess what that number is because the pattern was not clear at all. You can go back and check. And now it is clear why the pattern was not clear, because the answer to this limit is what? ln of 2. And what is ln of 2? ln of 2 means logarithm of 2 to the base e. And this is why it is clear we couldn't guess at all what that number is. Yes, because still we don't know what that number is. Yes. Okay, anyway, so I hope that you are not confused. The natural way of answering this question was to write this and try to calculate this limit, because this limit was above the level of high school mathematics. we actually took a journey around it, and then finally we were not able to answer this limit. We were able to go a little bit ahead and answer the derivative directly, but then compare them together to calculate the limit. Okay, so I want you to know about this, because sometimes in the national exam they might ask you something that you have to answer using this limit. So I want to answer this. Limit of a to power h minus 1 divided by h when h goes to 0. If a is positive and not equal to 1, the answer is ln of a. But in this particular case, even if a is 1, it works. Because if a is 1, what is this limit? If a happens to be 1.
It's gonna be
If a is 1, just answer it. 0. Yes, a is 1. 1 to power any h is 1. 1 minus 1 is 0. And if a is 1, what is ln of a? 0. So you don't need to be bothered about this one, because this limit also works here. So this I want you to know. So I would say that this answering this limit is a byproduct of what we are presenting here. So again, let me just try to relieve you a little bit, because you really don't need to understand. If you like mathematics, I really want you to learn that. But for the time being, you really need to know how to use that table. That's it. For the questions in the book and in the exam, you only need to know how to use this table properly. Yes? Okay, now let us take this last question mark away to make everything complete. So how can I answer that question mark? Let me clean the board and give people to think. Give time people to think about it. Yes, do you want to answer? So now the question is this. F of x is a to the power of c. X, a is positive, a is not equal to 1, c a constant. So we want to answer the question that what happens if I take the derivative? Yes?
You used the same strategy as before.
Okay, just tell me what to do.
So instead of a, you say
Yes, so a is what? E
to the power ln of a.
ln of a. So again, I will do the same thing. So instead of this a, I put that. So let me write a to power cx is equal to e to power ln a to the power of cx. So then what can I do? I can multiply these exponents. So this becomes e c ln of a and then totally x. Yes, is that right? And then what I can do, I want to differentiate this. So instead of differentiating this one, I differentiate that one because they are equal. Okay, and then I continue. Okay, how should I differentiate this one? A is a constant, C is a constant, so C times ln A is a constant, which plays the role of that constant C here in total, yes? So you can call this in your head capital C, for example, if you want to. And then e to power capital C times x prime, C goes down, but what is capital C? C ln of A. And the function repeats itself. This means that but for this one, I can take it because this one can be written more compactly like this. So I have C ln of A multiplied by that. So this becomes c ln of a multiplied by a to power cx. That's the answer. So I can now clean this and write the answer. So you see, c goes down, the function repeats itself, but you have to multiply by ln of a. So that is the answer. And as a byproduct, this is also good to write down somewhere in your notebook, yes. We already answered this when a is e, yes.
If you take the derivative of that, does it just become the same thing, just one more, like you take one more down?
Yes. Yeah. We will talk about higher derivatives later. Okay, so what I will do now, I will just present one example and stop teaching, and then we complete, because I just introduced you the natural logarithm. I want you to be able to solve some problems using natural logarithm. So I mean, there are some questions in the book that is not relevant to the derivative at all. So you need to solve logarithmic equations, exponential equations using natural logarithm. This part we will practice later. But let me just give you some simple examples to improve your skills about differentiation. So this is the end of your lesson here. We will complete this table in Math 4. 2 trigonometric functions and then logarithmic functions. So the derivative of the ln itself, we haven't studied that. So, and then of course, we will add 3 more rules here and some functions here. The rules will be finished in high school, but this table will continue when you go to university and when you start learning about new functions. So you can expand that table. Okay, so the last exam for today's lesson, the last example. Yes. So differentiate the following functions, yes? I don't know, let me start with a very simple example. F of x is 5 to the power of x. So if you want to differentiate this function, so you need to understand that you are supposed to use this formula. Yes? How do you know that this is not the second row formula? Because the base is constant and the power is variable. So that's an exponential function. So if you want to differentiate this function, what will happen? So the function repeats itself, but this is not finished. You have to multiply by ln of 5, and that's it. You don't need to put this in the calculator to calculate ln of 5. By the way, you know that on any calculator, there is an extra button called ln. So that's the meaning. So that's it. So number 2. So number 2, what should we do? Let me write some examples. So for example, f of x is equal to 3 to the power of x plus 2. You want to differentiate this function. So what I'm supposed to do?
It repeats and
Because this is a constant added this time. So what I'm supposed to do? Yes?
You can divide them into 3
times, yes. So what you are supposed to do first, you have to write it in this form. F of x is equal to what? 3 to the power of 2 times 3 to the power of x. But 3 to the power 2 is a constant, 9 times 3 to the power x. So now when I ask you to differentiate this, I don't want you to write this, but I want you to think in that way. This is the meaning. But this is a multiplicative constant according to this first rule. Here, you just write 9 and then multiply it by the derivative of this one. I don't want you to write this down. But this is the way that you have to think. Okay, but this one is now today's lesson, so I have a 9 here. And then the function repeats itself. And then you have to multiply by the natural logarithm of 3. You can keep it like this, or if you want to, you can combine these two back. It doesn't matter. This becomes 3 to the power of x plus 2, ln of 3. So that is the derivative of this function. Okay, one more. Number 3. What do you think will happen here? So f of x is, for example, 2 to the power of 5x plus 1 divided by 3 to the power of x. So this plus 1 is still on the power. I want to give you a little bit of time to think about this. This is the last example for today. The reason that it might be a little bit challenging because you don't know about the quotient rule. And I think the way that I designed it, you can actually solve this exactly using the information you have here, but you have to rearrange this in a proper way. Do you have any idea? So let me write it here. F of x is 2 to the 5x plus 1 over 3 to the x. Okay, so can you help me now to do it? Yes?
First we can write 2 times 2 to the power of 5x.
Yes.
Then instead of 2 to the power of 5x, we can write 32 to the power of
Exactly.
x.
Thank you. Because of course you might say that, okay, I can use the last row formula to do that. Yes, you can, but only for this one. But what happens for this? That's the only thing we can do. So let me write it in 2 steps. Instead of writing 2 to the power 5x, I can write 2 to the power of 5 and then to the power of x and then divided by 3 to the power of x. And then 2 to the power 5, as actually Ali mentioned, is actually 2 times 32 to the power of x divided by 3 to the x. Okay, but still it's a fraction, Ali, so how can we go for it?
So we can take out 2, then we can write 32 divided by 3, 2 in the
Exactly,
bracket.
thank you. Yes, that's the point. So that becomes 2 times 32 over 3 to the power of x. And now this fraction plays the role of a. Yes? Because, so let me just tell you what to do. So if I want to differentiate that, what do I mean? I mean differentiate this. This is what we mean. But this, I have to use the first rule. Yes, that rule up there. Let me see if I'm recording or not. Yes. So here, this one I am using. So 2 goes out. And then I have to differentiate this function only. I'm writing it so much because I'm writing too much actually. You don't need to, but I want you to understand what is going on. Now, do you agree that this one is an exponential function, yes? So if you compare this with that one, That is exactly an exponential function, but a in this case is what? So that's it. So then I can use this rule again, but giving the role of a to 32 over 3. So this becomes 2 is 2. The function repeats itself, but you have to multiply by the ln of the base. It doesn't matter if it is a strange number or what. So this is your derivative. Any questions? Thank you very much.